body. And with that reason in mind, that gives us good reason to believe that these will be very valuable in development of therapeutics for the treatment of devastating diseases with significant unmet medical needs. The company was founded 2 years ago by Dr. David Kern and Dr. David Schaefer. Dr. Kern, our CEO, is a clinician scientist and biotech entrepreneur with over 20 years' experience in the design and development of therapeutic viral vectors. Dr. Schaefer, our CSO, is a professor of bioengineering and the director of the Stem Cell Center at the University of California, Berkeley, and he's a world leader and pioneer in this field of AAV research. The platform technology is therapeutic vector evolution, and I'll go into more detail in a bit, but suffice it to say that the variants that come out of it form the cornerstone of our intellectual property portfolio. They've also given us a fantastic opportunity to work with some wonderful collaborative partners, as well as to set up our own internal pipeline of therapeutic products. The company is about 30 strong at this point, and we're located in Emory, California, which is next to Berkeley and just across the bridge from San Francisco. So a little bit more about the discovery platform, therapeutic vector evolution. This platform enables us to select for AAV variants that are capable of overcoming the hurdles that first-generation wild-type AAVs face. Now, when you think about developing a therapeutic, you think about the cell types you need to hit, you think about how you're going to deliver that viral therapeutic to get to those cell types, and you think about neutralizing antibodies that could shut that viral vector down before it gets to the cells of interest. So when we think about AAV and selecting for AAVs that have particular desired traits, we think about their ability to target a tissue. We think about their ability to target the tissue in the context of the route of administration that's the most clinically relevant route of administration, and we think about their ability to target that tissue even in the presence of naturally occurring neutralizing antibodies. These are the 4D MT vectors. So what is this platform about, and how does it work? Well, we begin with the wild-type AAVs, those are the primitive capsids, and we subject those AAVs to mutagenesis. This could be random mutagenesis. We insert peptides into particular regions. We do directed substitutions based upon ancestral nodes. We do capsid shuffling. And what that gets us to is about 25 libraries with various different mutations embedded in them. And from that, we get to, when we pool it, a master library of over 100 million variants. So let me just say that again. That's 100 million AAV variants. A lot of variants to choose from. So how do we identify the variant, which I've put up here in a little red dotted line, the variant that has the ideal characteristics for the therapy that we want to be delivering? Well, what we do is we subject that library through several rounds of selective screening. Take that library, you inject it into a non-human primate by the clinically relevant route of administration, harvest the tissue, harvest the genome out of the tissue, and create a new library. The library goes back into the non-human primate. Repeat the process. Do several rounds of selections, and over the course of those rounds of selections, you're actually enriching over time for the variants of the winners. These are the variants that are able to overcome hurdles, be they anatomical, be they cellular tropism, be they neutralizing antibodies, so that at the end of the day, you wind up with a small handful of variants. Now, what do you do with that small handful of novel AAV variants? Well, the next thing we do is we characterize them. So we've got our discovery team in place. 4D has actually developed some very great in vitro and in vivo capabilities to support this. On the in vitro side, we've built a team of scientists that are dedicated to culturing particular and rich populations of cells of interest. So they could be retinal pigment epithelial cells, as you see in the upper panel here, derived from induced pluripotent stem cells from humans. They could be beating cardiomyocytes, they could be primary hepatocytes, you name it. This group can also do complex cultures. As I'm showing right here, this is a retina cup, an eye cup. For those of you that are familiar with culturing these sorts of systems, that's out like 6 months that thing's been growing. And it's really quite an amazing feat to me to see the complexity in that tissue culture dish and how well that models what's happening in a human. The company's also built out its in vivo capabilities. We've got a fantastic Rolodex of CROs that are experts in various different tissues. And in addition to that, we've also built out internal capabilities to assess the tissues once they come out of those mice and non-human primates. This is depicted on the slide on the upper right. That would be a mouse retina after transduction with one of our AAV variants. And in the panel on the lower right, an in vivo image in life of a non-human primate transduced with another one of our AAV variants. So all in all, right now, we've got more than 10 discovery programs ongoing, with leads in a number of these programs as marked by the asterisk. So enough of the background. I'd like to move on and talk a little bit about the data. So what's up here is a schematic along the top of one of our lead discovery programs, this being our program in the retina, wherein we deliver the AAV vector to the vitreous, so the jelly of the eye, a really constructed place to deliver an AAV therapeutic for the treatment of conditions, retinal conditions. Each of the various different steps of the selection process is marked in a separate arrow, rounds 1, 2, 3, 4, 5, and 6. What I did not mention in my previous slide is that when we make that new library for that next round of selection, we can actually sample the library. So we can, in real time across the selection, assess how the pool is evolving, identify the dominant motifs that are coming out of it, and ultimately figure out when we've achieved convergence. So Melissa Cotterman, who leads our discovery effort, has been doing this in a number of different programs. As you can see here, the data demonstrates that in this particular retina program, we have achieved convergence by around round 4, round 5. Here's a great example of how you can monitor the pool. You can see that red pie chart. So the pie represents the pool, and the pieces represent a particular motif. You can see that red motif growing. It begins to take over the pool with each successive round of evolution. Now, here's an example of what we do next when we take that variant. In this case, Tanveer's vaccines group, the in vitro cell modeling group, has cultured up retinal pigment epithelial cells and transduced them with either the variant of interest from 4D, that's E4, or AAV2, AAV2 being the background for this particular variant. And what you're seeing in the upper panels, that's natural GSP. So the variant is clearly doing a better job at transducing the cultures, both the number of cells and the extent to which those cells are getting hit by variants. In the lower panel, that's a magnification of the retinal pigment epithelial cells. You can see ZO1 is a counter stain. This is a 95% enriched population of human RPE cells induced pluripotent stem cells. On the right panel, we give you a little quantification of that. We've got about a 5-fold increase, 6-fold increase in the expression levels of the percentage of CFP cells, in the culture over the AAV2 backbone, the parental, and you can see that is dose-dependent with increasing multiplicities of infection. Here's another program that we've got ongoing. This is a program that we're working on in collaboration with UCure, one of our partners, and it's for the discovery of variants that target the liver after IV delivery. This is interesting. This is not the slide. Okay. This is not the slide that I'd imagined, but it works for us. Again, you see the 6 rounds, and you see at the end of that the pie chart of representation in that slide. Again, going in vitro and looking at what's happening, we see that the variant 1 and 2, are doing better than the wild-type parental serotype that was AAV2 at transducing human primary hepatocytes that Tanveer's group is cultured, as well as other variants that people are using in the art right now as they approach the clinic, 88 and 89. Again, if we do that quantification, we see 4-fold or so, maybe 5-fold increase over the parental serotype, as well as the clinically relevant others. Okay, the last program we have here, this is the brain program. This is, again, with UniCure, and there should be, I apologize, a logo at the bottom that says UniCure. This is intrathecal delivery to the brain. Again, 6 rounds of discovery, and again, we see convergence where we've got now 1, 2, 3, 4 lead motifs, as well as a number of others marked in gray. Analysis of this population by looking at primary neurons, IPS-derived, shows superior transduction of the variant over AAV2 and AAV9. And there you see again. Our last program, which we've just gotten to the top of the presses, our variant 4 is the heart. So this is intravenous delivery to cardiac muscle. We were able to achieve convergence by around 4, and we are now in the process of manufacturing those molecules and delivering them to non-human primates as well as to cells in vitro. So here's a list of our programs in discovery and where we're sitting with them. I should add that these programs require an awful lot of manufacturing capabilities.